one of the main contributors to the area of logical learning and monotonic reasoning, which most of us work. Mirek is from University of Kentucky. Kentucky was for many years, nearly 15, I think.
Nearly. Fortunately not.
the head of the department there. So it's a good example for Sergio. And well, he gave a major contribution not only to our specific research area, but also in graph theory, discrete mathematics, and to AI more in general. I mean, he is one of the authors of the book Non-Monotonic Logic, the title, and I appreciated many of his results, for instance, on auto-epistemic logic. It was a very important JCM paper that gave a very relevant contribution. Well, I don't want to list the many contributions he gave. I mean, one thing that I particularly appreciate is that he was one of the first who understood that, who proved the quality hardness of reasoning with understandable model semantics that all of us very often refer. So it's a pleasure that Mirek is here, even if for a short period of time. But he was so kind to give 2 seminars. So today is a more funny seminar, Sudoku, games, etc. Then on Monday there will be one more specific for our area. So I take the opportunity to announce also the next seminar that will be on Monday at 5 o'clock here. Thank you again.
Thank you very much, Nicola. It's very nice to be here. You say it's a pleasure for you, but it's even bigger pleasure for me to be here. I can assure you that. I am enjoying this stay very much, and I wish it would be longer. Today I will talk to you about Sudoku, and I say it's fun and science, and I do hope it's more fun than science, but still there will be a little bit of science in it as well. So let's look at it. Why is Sudoku so popular? Well, it's very simple. You have 9 digits and you have a grid and that's all you have. Well, not quite. You also have some squares already filled in with these numbers 1 through 9. And now the goal is to complete. You see those original clues are in red here. And you have to complete all the remaining cells, fill them with numbers, so that no number in a row repeats, and no number in a column repeats, and no number in a block repeats. So it's quite simple. Pencil, paper, of course on that paper you have to have a grid and numbers already filled in. And then you can play with it. I already mentioned that to some of you that I never leave home without a Sudoku with me. Here is one that I'm currently working on. Okay. We have, and I will talk about that a little bit, we have designed a system based on our software for essentially doing cancer set programming. That every day produces 1 Sudoku and displays it online, so I can print it always down and then work on it during the day. Especially good at meetings, I will tell you. Okay, so here is what I will be talking about today. I will give you a little bit of history of Sudoku. Then I will cast Sudoku as a constraint satisfaction problem. It turns out that probably it's better to view Sudoku as an answer set programming problem. I will focus here on propositional logic or logic of propositional schemata, but let's think about that satisfiability. But you can approach it from the point of view of logic programming as well, and you will see where the difference is between the 2 treatments, between the 2 approaches. People are mostly interested in solving Sudokus, that's where the fun is, but we were interested in actually generating Sudoku, using our tools to to generate Sudokus. I'll mention a little bit about complexity. I'll give you an outline of an NP-completeness proof. I mean, the proof will be complete, only I will not show you NP-completeness of the problem from which I will construct the reduction. Very interesting problems arise when you think, when you consider counting how many different Sudokus there are. So again, I will probably not have enough time for all that in detail, but I will just outline to you that there is very interesting stuff related to counting Sudokus. Now, there are variants of Sudokus, of course. They differ in what sorts of constraints we impose on the problem. And I will have some conclusions, some discussion, some open problems, because even though I cannot perhaps formalize all of them, it seems to me that Sudoku does open several interesting, maybe not research directions, but at least directions for some thought. Okay, so first, very quickly about history and some trivia related to Sudoku. This invention is attributed to Howard Garnes. He was a US architect. Apparently, he invented Sudoku in 1979. Nobody really knows exactly that he is already dead, unfortunately, but the first puzzles were published in a logic puzzle magazine, Dell Journal it's called, published in the United States. And trying to trace back the inventor of the Sudoku, what people later did was essentially this. They looked at all issues around that time, and they realized that whenever Sudoku was published in an issue, Howard Garnes was one of the contributors. And he was never a contributor whenever Sudoku was not published. So that way, indirectly, they inferred that Howard Garnes is indeed an inventor. Okay, in the United States it used to be called number place, but then, of course, the name Sudoku gained popularity. Okay, not much perhaps has happened with Sudoku for quite a while, but in mid-1980s it gained popularity in Japan. So it's not really a ancient Japanese game, it's just that in mid-80s it gained popularity in Japan. There is a magazine, Nikoli, which is a puzzle magazine in Japan. They actually trademarked this name, Sudoku, which stands for Sujiwa Dokushin Nikagiru, which roughly means the numbers must be single, in a meaning unwed, that means not married, okay? And the idea is that two numbers in a row would be married, or two numbers in a column would be married. That was shortened to Sudoku. And of course in Japan, in this journal especially, they publish handcrafted Sudokus. So in addition to the constraints that I mentioned earlier, they are also very interested in having some sort of an aesthetically appealing design of the game, some nice symmetries. We were never interested in these types of symmetries, although they can be coded into answers and programming programs, and we could produce symmetric Sudokus as well, elegant Sudokus as well. Well, there is an Italian accent here. I'm not sure how many of you were aware of the fact that the first World Championship was held in Lucca in March in 2006. Then the next one was in Prague, in Czech Republic, and I don't know whether 2008 championship yet, whether it was held, will be held, or maybe people gave up on the championships because they are too hard and nobody can win them. Okay, so we will now go on to terminology. I used this terminology already several times. Well, that's a grid. That's a row. Here we have a column. Here is a block. This is a band. And this is a stack. These last two terms will be used later on when we will be talking about counting. Now, we are interested in good Sudoku instances. And a good Sudoku is a Sudoku, that means a grid partially filled with digits 1 through 9, that has exactly one completion to a fully filled grid. So that's a good Sudoku. If there are more solutions than one, not very good Sudoku, because at some point you can just put perhaps one of several choices and you still will be able to continue. And of course, if there is no Sudoku, it's unfair. You work so hard, you think you may never finish actually with Sudoku because you always think that you are missing some obvious clue. Okay, so that's a brief introduction, and here we now are at the point when we will look at Sudoku as a constraint satisfaction problem. Well, it can be viewed as a constraint satisfaction problem because you have 81 variables there. Each position gives rise to a variable. For each of these variables, you have a domain. All domains are the same. They take values, each of these variables from 1 to 9. But 1 through 9 have no meaning, no importance, no significance for basic Sudokus, classic Sudokus. It could be actually any 9 symbols. The fact that they are digits plays some role in extensions, variants of Sudoku, where arithmetic is added to some degree. Okay, so here we have variables and domains, and to have a constraint satisfaction problem out of that, we have to have constraints. So you remember, each row has each number only once, each column has each number only once, and then at that point you know that Sudoku is really a very special Latin square, because these two constraints define combinatorial objects known as Latin squares. So here is the distinguishing constraint. Each block must have each number only once. Okay. So since Sudoku can be viewed as a constraint satisfaction problem, now the question is, can constraint satisfaction techniques be used to solve Sudokus? And of course, the answer is yes, they can. You can do it using actually what's known there as propagation rules. So here you have basic propagation rules. I used the term local here for a reason. I will explain that in a moment. We have two basic propagation rules. If a digit can be placed in only one square, in a row, column, or block, it is placed there, right? So you have a row, for instance. Some elements in a row in this row are already filled with digits, and some other are not. But the digits are placed also somewhere else in the grid, and they preclude placing, let's say, 1 in any of the 3 positions except for 1. Well, then this 1 has to go into this cell. That's what this constraint tells you. If a square can consistently accommodate, if a square, if a square can consistently accommodate only 1 digit, meaning there is all the other digits cannot show up there in this square because they would evidently violate one of the constraints we already have. They show up somewhere else in the row, somewhere else in the column, or somewhere else in the square. Then obviously this square must get this only 1 digit that is not yet excluded. These are local propagation rules because to determine that the number is to be placed in a cell doesn't require any complex analysis. You just look at this square alone. If you keep track of what's still available for that square, for instance, you immediately see at some point that there's only 1 element available there. So they are local. Sometimes you have to look at these 3 the structures associated with a cell, but that's pretty much it. We will be talking about global rules as well. Now you have block row and block column rule. What is this rule about? Well, this is the following rule. If a square must be placed in one of the locations on the intersection of block and row, or block and column, then of course it will never appear anywhere else in that row or in that column. So sometimes I don't have, unfortunately, I realized later a diagram for it. But you have this row, and this row intersects a square, a block, sorry, and you know that a digit must show up, 1 must show up in one of the 3 squares on the intersection. You don't know where, but you know that it has to show up somewhere there. Then you know that it cannot show up in that row outside of that block. So here you cannot fill in the square. You don't put any number yet anywhere. This just excludes certain locations for a digit. Still a local rule, by the way, because you look only at the block, you look only at the row. Now here are very interesting rules, K in K rules, and the idea is roughly this. If you have K squares in a column, or in a row, or in a block, K squares, and if these are the only squares some K digits can be placed in, then of course these digits cannot be placed anywhere outside of these K positions. And conversely, any other digit can be placed in any of these K locations. So this is somehow related to pigeonhole principle, and that will have a little bit of significance later.
And
so
does this correspond to what you find in the literature called as naked pairs of triples?
I will confess that I have no idea how people call these rules, Sudoku people call these rules, but yes, people invented lots of these rules, for Sudoku. So I will be trying to use the terminology that is more aligned with what people with formal mathematical education would use. Okay, so here is the illustration of this K in K rule. You have the following situation. In this block, these three squares are already used up by some digits. You have 3 and 2 placed here, 3 and 2 placed here. So you see that these two squares are the only two squares for 2 and 3. You don't know whether 2 is in the corner or here, or whether 3 is in the corner or here. That you don't know. But you know that 2 and 3 must be in these two positions. Then you, for instance, know that 2 cannot be here. Of course, you knew before that 2 cannot be here because of that 2 here. And that 2 in this block precludes 2 from anywhere here. But this is this new information you are getting from that particular rule. 2 cannot show up here. And similarly, 3 cannot show up here. So that's a propagation rule that allows you to eliminate some domain values for some variables and make the problem simpler. Okay, so these are really rules that are relatively local, meaning you can look and you can have everything in your mind. You don't have to write anything down on paper. You probably will still remember that. Relatively local reasoning, and you have some new information about your Sudoku. But this is a place where we can draw inferences based on a slightly more complex reasoning. In fact, one could say global reasoning. So here is a rule. I say local with question mark. Question mark means maybe it is still local because, as you will see, the reasoning involved is polynomial time. But whether any human is able to perform this local reasoning is questionable. So what are these rules? Well, these rules look like this. If placing digit x in a particular position y cannot be extended to consistent placement of 9 copies of x, then of course x cannot be placed in y. So you'd like to find positions. In order to use this rule, you look for positions which have the property that you place a digit there. There is no way to find placement for the remaining 8 occurrences of that digit. And similarly, if placing a digit in a cell within a row, column or block couldn't be extended to a completion of that row, column or block, again, y is not a possible location for x. But the reasoning which allows you to derive this conclusion, that placing x in y doesn't extend, somehow is no longer local. It really takes into account, essentially, in principle, the whole Sudoku, the whole grid. So, yeah.
I'm a bit confused about the slide, the previous slide.
Yeah.
This one. Why we can put 2 and 3 on the 1, 2, 3, 4th line?
On this line?
On the same column, okay, the first column.
Here?
Okay, but the 4th line.
Here?
Why not?
No, we can place 2 or 3 here, but we will not yet place 2 or 3 here because I cannot say anything about what can or cannot be in this square, right?
Okay.
because I am not sure about the position of 2 and 3 here. So if 2 is here and 3 is here, then 2 cannot be here and 3 cannot be here. If it's the other way around, then that means 3 is here and 2 is here. Then 3 cannot be here and 2 cannot be here. Okay? So this rule only tells me that, well, I know one other thing here. Do I know? No, that's all I know. That's pretty much all I know here. If I have this situation that I showed you here, about 2 and 3, all I can infer, in addition to what I knew before, is that 2 cannot be anywhere here and 3 cannot be anywhere here. That's all I can infer. Ultimately, it may turn out that 2 is indeed in the corner, so 3 will end up here. Later I will find that out, but not now. And I want really to encourage you to ask questions, because some of these rules will become quite intricate, so we will get lost. I am getting lost each time I am thinking about that, so it's better to be careful here.
These rules are a possible choice of rules?
No, well, when I am solving Sudoku, I have whatever I can take.
Just a minimum size of rule that you can use to...
This is a very good question. I will come back to this question, okay? All I am doing right now is not telling you which rules people use when they solve Sudoku, or which rule I use. I am now trying to figure out in what way we can propagate information that we already have to other squares. I also am trying to pay attention when describing these rules, how hard is it to apply them. So the first rules I described, the basic rules, are very easy to use. Okay, you look at a row, for instance, and you realize that only one place in this row is left for 1. Well, then obviously I will put 1 there, right? So these are relatively simple rules, and everybody uses them. All these more complex rules, who knows? And you will see even more complex rules here as well. This one actually is one of the more complex. Okay, so how such a difference could be made? One more time. If I want to find a location which has the following property. Placing x there gives me a disaster. I cannot anymore continue. And I will focus on this rule. This is very similar. It turns out that it's related to the problem of finding matchings in bipartite graphs. So what do we have here? That's why these rules are called matching rules, because they are related to matchings in bipartite graphs. So vertices are rows, columns which do not have x. In our example, we will have that there is no x anywhere, but in principle you may already have some x's placed, and you are not really looking for the placement of 9 x's in 9 different squares, but whatever the number of x's remains. But that's a minor detail. So we have vertices, there is a typo, sorry. Vertices and rows are rows, columns without x. One group in this bipartite graph are rows, the other group of vertices columns. 2 vertices, column C and row R, are joined with an edge if you can place x on the intersection of the row R and column C. I will illustrate this procedure, but I will go through it. Then you find the perfect matching in the graph. Once you have a perfect matching, and by the way, there is a polynomial time algorithm to find the perfect matching in a bipartite graph. Perfect means it has to cover all vertices in the graph. So once we have the matching, we orient the edges from rows to columns. That's arbitrary choice, but then you have to be consistent. You orient the other edges from columns to rows the other way around. Then you find strongly connected components, again polynomial time process, and then edges that are non-matching edges that connect different strongly connected components cannot be used for x. You will see why in a moment. So you see, that way, if I find such non-matching edges that connect different strongly connected components, then I will have positions where x cannot be placed. According to the rule, these are forbidden for x. Alright, so by the way, this whole method doesn't take into account at all block constraints, so it would apply to the problem of completing Latin squares as well. And we have similar matching connection for the second rule, which I will not discuss because, as I said, it's similar. Okay, so here you have a Sudoku. You haven't placed x yet anywhere in it, but you've placed some other digits. So all these red lines mean that some of these cells, squares, are forbidden. Okay, if you look at that, now you have this bipartite graph. You have rows 1 through 9. You have columns 1 through 9. And for instance, I have edges from 1 to 6, 7, and 9, because you see 6, 7, and 9 are the only places where x can go in row 1. And similarly, 2 is connected only to 1, 2. Okay, because these are the only two positions. And 8 is connected to 2, 3, and 4, I hope. 2, 3, and 4, yes. Okay, so now out of this, you have a graph. Then you look for a perfect matching. So I found the perfect matching here. It's now in blue. All vertices covered. No vertex has 2 edges. It could be found, as I said, in general in polynomial time. Okay, now we have edges of the matching. These edges of the matching might be viewed as places where you could possibly place x's, of course, because there would be no conflict. Since it's a matching, there would be 1 x in each row, and of course 1 x in each column. If this was not a matching, I would have 2 x's in a column or in a row, and if I have 2 x's here, for instance, here x and here x, then of course I have selected 2 edges that join in row 2. Okay, now I direct, as I told you, matching edges from rows to columns, non-matching edges from columns to rows. Okay, that's still relatively legible, but now I am looking for strongly connected components. So it's impossible to see perhaps all of them, but you see some of this red thing is a strongly connected component. Okay, so you look for strongly connected components, and I redrew everything. You have 3 strongly connected components here that are non-trivial. Here, this is a strongly connected component, and this is a trivial single element strongly connected component. This is still a matching edge. You remember that there was an edge from 8 to 3 because there is nothing of here actually. There was nothing, and we could put x into that position. So I found strongly connected components. Now, because of the nature of this graph that I've constructed, strongly connected components will have exactly the same number of rows and columns in each component. So you see each of these strongly connected components, non-trivial ones, have the same number of vertices here and here. Why? Well, because if you start going down and reach this vertex, you are necessarily having to reach this vertex as well, because the only way down is along a matching edge. So you cannot have a different number of vertices here than here. So it will look like that. And now in this example, I have 3 edges that are non-matching edges that connect different strongly connected components. What would happen if I place x here? Well, if I place x here, then x is no longer possible here. So this vertex is taken. This is a strongly connected component. This is the whole graph, as you have. As you could see, look, if this vertex is taken, can I still find the perfect matching? No, there is no way to find the perfect matching because you don't have a perfect matching in what is left here. See, I took away this node from that strongly connected component, and there is nothing else that connects this strongly connected component to the outside world. So I have 2 nodes here and 3 nodes here, so there won't be a perfect matching anymore. Putting x here kills a possibility of a perfect matching in this particular graph. There is a little bit, and consequently, these 3 positions are actually forbidden for x. See, I did a lot of reasoning here, constructed a graph, found the perfect matching, oriented the graph in a certain way, found strongly connected components. I worked a lot. As a game, I have 3 positions that I can say for sure x does not go to. So that's a fairly interesting rule that one could say is still an easy rule because I can do it in polynomial time. As opposed to, for instance, I could simply do exhaustive search. Can still this x be placed everywhere else consistently, that would not be a reasonable rule, quick rule, because it would be exponential in the worst case. Okay. Well, so I am fairly certain nobody is capable of using these rules, solving Sudoku. It's beyond human cognitive capabilities. There are now still fairly complex rules that perhaps masters of Sudoku can use it. Here is a rule called non-repetitive cycle rule. So what is this rule? You create a graph. You have a partially filled Sudoku already, so there may be many numbers everywhere else. But you realize that you see edges in this graph are connect squares and when. So edge with label x connects nodes that are only two possible squares for that number in that row or column. So in that row, 6 can only go here or here. This is frequently the case when you solve Sudoku, that you find such a situation. There are only two positions for 6 in a row or column. So here I have such a graph. There may be many other such edges in this graph. This is not all of the graph, part of the graph. But this graph happens to be a cycle, and it's not repetitive because you see every label here appears once. So there is no two consecutive edges with the same label. And what can I infer now? Well, I can infer that 5 and 6 must be here. Okay? That this top row must contain 5 and 6. I don't know if 5 goes here or here. I don't know if 6 goes here or here. That I don't know. But I do know that 5 and 6 occupy these two upper locations. Why? Well, because if I place 6 here, and I must place 6 either here or here. If I place 6 here, then there's only now one place left for 5. Remember, these are the only two places in that column where 5 can go. 6 takes this place, so 5 goes here. Then 2 must go here, 3 must go here, 5 must go here, okay? 6 and 5 in top row. If I do it starting with 5, I don't have that illustration here, of course, but if I have 5 here, then I must have 6 here, then 5 cannot be anymore here, so 5 is here, 3 is here, 2 is here, and the same story, 5 ends up here. A repetitive cycle. This is slightly different. You see, this is the same story as before, except that now you have two edges, consecutive edges with the same label. Now I claim that 6 must be here. Why? Because if not, the only place for 6 in this row is here, the only place for 6 in this column is here. So 6 will be here and here, if I don't have 6 here. Then of course I can infer 3. It must go here. I can infer 2. It must go here. And now there is no place for 5 anymore in that row. So that's a contradiction. 6 indeed must be in that cycle, in that square, sorry. Conflicting path. Very similar principle. The idea here is to have a path in that graph that is formed in the way described here. Edge with label x connects nodes that are the only two possible squares for x in a row or column, or block. And we have again on that path two consecutive edges with the same label. And we have, and what else we have? And we have this situation that the ends are labeled the same way and end up in the same block. So you see that the ends of the path are labeled with the same label, and the ends end in the same block, row or column, in this example block. I must have 6 here, because again, if I don't, 6 sixes must be placed here. Now 5 must be here and 3 must be here. And now 2 are forced into these last positions on the path, and they happen to lie within the same block, and it's over. It's a contradiction. So 6 indeed must be placed here. Okay, so these are, and there are more rules of that sort, but you have now some idea about the variety of rules and propagation rules that you can develop when you think about Sudoku in terms of constraint satisfaction. So what can you do with those rules? Well, surely you can solve Sudoku. You can pick some of these rules or all of these rules, implement them in a constraint solving program, and essentially the program will work as follows. We'll apply the rules to cross out domain values which are impossible anymore for a particular square, for a particular variable, as long as you can. And of course, if you get stuck at some point, then your program is too weak to solve that Sudoku. And if you are not going to get stuck, if you won't get stuck, then of course you will solve the Sudoku. With those rules, we can also generate the Sudoku problems. I will talk about that in a simpler setting in a moment, so I will not discuss that much. And you also perhaps can control difficulty of Sudoku. If you have to use very complex set of rules to solve or generate the Sudoku, then the Sudoku perhaps is hard. If you use only very simple Sudoku rules, maybe then Sudoku is simple. But you see, analysis of the difficulty of Sudokus, if you view everything here from the point of view of constraint satisfaction, is not easy. I presented many rules to you of various degrees of sophistication. Are they all necessary? Do we need to use them when we solve reasonable Sudokus or not? So it is a difficult setting to study basic problems about Sudoku, problems of difficulty, for instance, or problem of what is sufficient to solve a Sudoku. So I already mentioned that. Some questions. Did we describe all the rules necessary? Can we now solve all Sudokus without guessing? I don't know actually. I suspended for 9 by 9 years. Are these rules necessary? Surely some are not. You can solve Sudokus without them. But as I said, this is a very complex set of rules. Some of them extremely sophisticated, like the one with matchings. And we would like to have a simpler framework. Okay, so now I will look at a simpler framework. Here Sudoku will be represented as a sub-problem or as an ASP problem, you might say differently. Why is it good? Well, because suddenly within sub-framework or ASP framework, the rules, the propagation rules, become extremely simple. Essentially, the basic propagation rules are just unit propagation, right? Very special type of resolution. You can throw into this Boolean constraint propagation also look ahead. Then the rule becomes extremely powerful. Or you can think of hyper-binary resolution and so on, more refined versions of resolutions. You can even think of resolution as such, but then you know that resolution often requires exponential proofs, like pigeonhole principle. In order to prove inconsistency, you would have to have an exponential resolution proof. So that takes you away from rules that are easily understandable by a human and perhaps executable by a human. Still, Sudoku and simplicity of the sub-formulation allows you to analyze Sudoku much better perhaps than constraint satisfaction. Just a quick reminder. So what is BCP? Well, as I said, unit propagation. So you have a literal, that is its dual, beta is a literal, you have a clause like that, for instance. If you have a clause like that and alpha, then you will have beta. Beta here, you can think also as a disjunction of literals. Single application of this unit resolution would shorten the clause by one element. And you can do this process, this unit resolution, not necessarily, as I said, with binary clauses, as long as you can. At some point you get stuck, then you cannot propagate anymore. Here is a simple example. You have a rule with clause with 3 literals, 2 literals, and 1 literal. You need a clause with unit literal to start. First step, you obtain B. Now you have not A and B. You cannot derive C, and that's it. You cannot do anything else. With look ahead, it's like BCP. Only when you get stuck, you will pick unassigned literal, and you will perform BCP assuming this literal holds. If no conflict reached, then you didn't get anything out of that work. You pick another literal, possibly the same literal but negated. Otherwise, you infer negation of the literal because you know that alpha, if you do get a contradiction, you know that alpha was incorrectly selected. And here is an example. You have 4 clauses that give you a contradiction. BCP cannot even start, but if you are allowed to do look ahead, you will derive contradiction. Because you can, for instance, assume A, and if you assume A, then you will derive not B, right? Having not B, you will derive not A, and that's the contradiction. And therefore you know that assuming A was wrong, so you infer not A. But if you infer not A, then you can infer B here and not B here, and you have another contradiction, and you're right. So it's a more powerful inference rule. Just as an example, this BCP, this hyper-binary resolution, what is that? When you have a set of binary clauses, all of them with the same literal here, but with different literals here, and you have another clause of that sort. It's in one step you, in a sense, perform lots of resolution steps, binary resolution steps, and you can derive alpha or gamma, okay? Because all these betas cancel out with those, and you collect gamma and alpha. And that, in particular, is stronger than doing binary resolution as long as you can on all two clauses. Okay, here is how Sudoku can be formulated in the language that we developed in Kentucky, answer set programming language, but you will have very similar representation, I am pretty sure, conceptually at least, in DLV. The difference, why I wanted to do it in this syntax and not in logic programming syntax, well, because this system we developed in Kentucky is based on propositional logic, essentially. We do have these cardinality atoms there, but there is nothing non-standard really about the semantics as long as you deal with propositional grounded programs already. It's good because I still have this handle on propagation. When you use logic programming systems, you have to very carefully think what sorts of rules you use when you propagate during set, for instance. What sorts of rules these are. Okay, so we have such an encoding, and essentially you see this tells you that you have for each cell you have one number, for each column and number you have precisely one row, and so on. So we can either now use this to play with Sudoku, this statement, or we can get rid of cardinality atoms in a standard way and rewrite them into clauses. So for instance, exactly one of these 9 propositions must be true, is converted into one long disjunction and lots of short disjunctions which make it impossible for the same cell contain 2 different numbers in this case. There are also more sophisticated ways to compile arrays to the Boolean constraints, but we don't use them because that changes dramatically the way in which propagation works. Okay, so what can we now do with Sudoku if we think in this particular terms? Well, so let's look at this 2 in 2 rule that we had before. Can I, in the SAT setting, in a sense, simulate it? Well, the fact that I know that 2 and 3 are here essentially is captured by this well, there is a mistake possibly. Oh, no, that's not a mistake. That's one of the 2 rules. 2 is in 1, 1 or 2 is in 1, 2, and we have something similar for 3. So I have 1, 1, 2 or 1, 1 or 1, 2, 2, and there is something similar for 3. How do I know that there cannot be 2 here? Well, if I had 2 in 1, 5, I would assume it. And then, so this is my assumption. I have that clause which says that 2 cannot be in the same time in row 1, in column 5, and in column 1. So I have that clause. I made this assumption, so now I am deriving that 2 cannot be in 1, 1. In a similar way, I can prove that 2 cannot be in 1, 2. I have this disjunction, and now I have a conflict. So you see, when you think about Boolean propagation, at least some of the rules that we talked about before in the context of constraint satisfaction are very nicely simulated or subsumed by Boolean constraint propagation in this very simple setting. So the question is, are these rules as powerful as CSP-based rules? So, okay, repetitive cycle rule. BCP, by the way, is quite weak, just unit propagation, but subsumes basic rules in particular. So when you just do Boolean constraint propagation, standard unit propagation for SAT, then it already subsumes these basic rules, 2 first rules for solving Sudoku as we cast them as CSP problem. If you go to BCP with look ahead, then it becomes very powerful. For instance, it subsumes this repetitive cycle rule, conflicting path rule, block row, block column rules under some restrictions. So already BCP plus look ahead becomes quite powerful. And for instance, how do we simulate, or how do we show that we can make the same inference as we made there with repetitive cycle? If we assume that 6 is not here, then we can, based on the constraints, other constraints we have, then we can infer this, because we already, as I said, the 6 means we already know that 6 is either here or here. So we have a binary clause which tells you the only two locations possible for 6 in this row and in this column. So since we assumed that, we now, by means of just binary propagation, derive 6s. And then, in a standard way, we derive 3 here, 5 here, and we get a contradiction. There is no place for 5. All this involves unit propagation once we've made this assumption. Okay, so that leads to a contradiction. Consequently, we can derive that 6 actually must be placed here. So that shows you that once you have look ahead in your propagation, in your basic Boolean constraint propagation, you have a very powerful inference rule. So BCP plus look ahead, however, does not seem to be strong enough to imply non-repetitive cycles. Something more is needed, nor those block row, block column rules if there are 3 or more possible locations involved, nor the K in K rules. And hyperbinary resolution is a little bit more powerful, or we can do a little bit better. But still, of course, we would have to have even more complex propagation rules if we wanted to simulate all rules we have invented for the constraint satisfaction setting. Of course, I already mentioned that when you have this K in K rules, they essentially say these K things have to go to these K cells. And now if you think, oh, I will place one more element into this K plus first digit into these K cells, you want to get a contradiction. Well, that's like showing that the pigeonhole principle is theory encoding pigeonhole principles is contradictory. Resolution-wise, even with full resolution, you need to have an exponential vector proof. So obviously, these rules are very hard to simulate in general by resolution type systems. So, of course, polytime versions of resolution not sufficient. They will fail at some point for big Sudokus, not 9 by 9. But of order 3 Sudoku, those 9 by 9 Sudokus, who knows? Perhaps they are good enough. As with constraint satisfaction, once you develop all these rules, essentially BCP alone or BCP plus look ahead, you can use them to solve Sudokus. Can they solve all Sudokus? Let's say all 3 by or all 9 by 9 Sudokus? Well, that's one question. We don't know. I will make this question more formal in a moment. Right. So we can use them to solve. But we can also use them, and that's more interesting, maybe even to generate Sudokus. So how do we generate Sudokus? So now I am switching a little bit. We talked about propagation rules. We know what they are. Now how do we generate Sudokus? First, how can we even fill out the complete grid, not paying any attention to clues that we may have? Okay, I will show you how to construct one example of a filled Sudoku using ideas that we have for Latin squares. So how can I construct a Latin square? Well, I can start with a permutation. If this is my permutation, by alpha I will denote this shift. So here's a very simple algorithm to generate Latin squares. Start with a permutation of n numbers, and I am now talking about n by n. And of course, I put shifted permutation in row I. So 1, 2, 3, 4, 5, then I shift, 2, 3, 4, 5, 1, then I shift again, shift again, shift again. That's a Latin square. No repetition, no repetition, no repetition, no repetition, no repetition, and so on. I can also do it indirectly by perfect matching algorithm. I can start with any permutation in row 1, and then the next row I can fill out by finding a perfect matching in a certain graph. Then I have row 2. I reconstructed the graph, apply perfect matching algorithm, and I can get the third row, and so on. So we have another method to generate Latin squares. But how do we... Sudoku grids are a bit more complex. Direct construction is as this. You pick 2 permutations of 1n. Alpha, this is now a size of the small block. So Sudoku is n squared by n squared. You pick one permutation and the other permutation, and shifts alpha I and beta j combine into a block ij. So here is the picture. I have one permutation 1 to 3, and I am applying shifts. Here I have 1 to 3, the same permutation here, but it shifts here to 2 3 1, and here to 3 1 2. This one 2 3 1, 3 1 2, and so on. So one permutation 1 to 3, the other 1 to 3. As we go this way, 1 to 3 shifts. As we go this way, 1 to 3 shifts. And now this block, for instance, is obtained from the second shift of this and from this. So we have 3, because that's the second shift here, 3 1 2, 3 1 2, 3 1 2, and we combine that with 2 3 1. It's very easy to check that you cannot have a repetition anywhere in a row, column, or a block. So that's a Sudoku. Okay? There is an explicit construction of a Sudoku for every order. Okay. That's very needed when you want to generate Sudoku. Because those good Sudokus, I told you, are characterized by the fact that there is only one completion. But a better Sudoku is if the completion can be reached by simple rules, not by exhaustive search. Right? But by something that you can do in polynomial time on a computer, or that you can easily do in your head, perhaps, if you deal with those small Sudokus. So good Sudoku is just this, better Sudoku is just this, and how can we construct them? The algorithm is here. But first, what is simple reasoning? Well, it must be forced by givens, and it must be based on simple rules, local propagation rules, not by exhaustive search. In case of SAT, you will want Boolean propagation rules only. Possibly look ahead, maybe that a human can still manage, but I am not quite sure. As I just say here, not many humans can do this complete, this look ahead in their head. But certainly you don't want backtracking or exhaustive search as the basis for your simple reasoning. And now, to generate a grid, you need this, a completed Sudoku grid. So we have seen how to construct one. And a reasoning algorithm for Sudoku, some set of rules that you decide on. And then you will work as follows. You start with a completed Sudoku, you will find a non-blank square, and you remove it. And after removing the single clue, you will apply your reasoning algorithm. If your reasoning algorithm, based on the rules you pre-selected, can solve that Sudoku, well, then this set of rules is sufficient for that Sudoku. You can go on, take away another clue, and make sure that your reasoning algorithm still can solve the Sudoku, and so on, and so on, and so on. At some point, you get to the place where removing clues don't allow this reasoning algorithm to solve what you have. And there is no way to make it smaller. Removal of any clue gives you a problem which your reasoning algorithm cannot solve anymore. Okay, so just at the moment when it lasts good, you have a Sudoku that its difficulty is characterized by complexity of this reasoning algorithm. And the simpler the set of rules you use to generate it, the simpler the Sudoku, the harder the set of rules you use to generate it, more complex, more sophisticated, presumably the harder the Sudoku. As you will see, there is not really that much of a room here in a moment. So what we do, we use our grounder, which does unit propagation as part of grounding. Okay? This grounder has two options. Either it only uses Boolean propagation, this unit resolution. So it really simplifies the program very little. The propositional CNF theory very little. Or it has an option of enabling look ahead. All Sudokus that I am solving, that I showed you a moment ago, for instance, I really generated only with the help of Boolean constraint propagation. And already this Boolean constraint propagation gives you Sudokus that are quite interesting as puzzles. Give you a lot of challenge, give you a lot of pleasure. So even the simplest possible set of rules gives you Sudokus that you enjoy. But we can, of course, instead of this reasoning algorithm, use look-ahead version of BCP. Then you get very hard, unfortunately, Sudokus, where you do have to make guesses, and I, for instance, often get discouraged. I try to solve it, and I am able to go on to a certain point, and then I know I have to make make a guess, or because sometimes I stare at it for 2 hours or 3 hours, and I know I have to make a guess, but I don't know where. So I make a guess, but it is a wrong place to make this guess. You make this guess, but you cannot propagate a lot from that guess. So you are unhappy because you already marked on your paper something, and I never use pencils, so I never can erase. I only can cross. So at a certain point, when there are too many strokes, I know it's hopeless, I throw it away. Okay, so there are only these 2 versions that we generate, only 2 different types of reasoning algorithms. And already you have this situation when on one end you have very nice puzzles, on the other end you have puzzles that are still, I think, quite interesting, but occasionally may frustrate you. Okay, so one last point is the starting point. You don't want always to start with this one single Sudoku that I generated, because that way you will have only a fairly restricted class of Sudokus that you will generate, because they all start with the same final configuration. So it's much better we have a local search solver which solves this set of constraints and finds a fully filled Sudoku. The largest that I could solve was 49 by 49. We couldn't ground bigger Sudoku. Well, here you have grounders that perhaps can handle 64 by 64 Sudoku, I don't know that, and then solve that Sudoku by DLB. That should be very easy. Once you ground it, I don't believe that DLB will have any trouble solving it. If you manage to do it, then you have an easy way to start generating 64 by 64 Sudokus. Of course, I guarantee you that no human will ever solve them, but so you will not be able to sell them, that's for sure. But it's certainly fun, and for benchmark for grounding, I think it's a good problem. Difficulty, I already commented on difficulty a little bit here. The more elaborate rules, the more difficult Sudoku is, but it turns out that at least for 3 by 3, there is not a lot of variability. You can get either reasonable Sudokus or right away fairly hard Sudokus. Okay, this is a very interesting problem. What is the minimum number of hints or clues that still guarantees that you may have a good Sudoku? Well, current record is 70. And it's been for many years. Let me put it carefully. No grid filled with 16 numbers, no grid with 16 squares filled has been found so far that would have only one solution. All these grids would either have no solutions or many solutions. Of course, no solutions if you start very stupidly putting them in conflict somehow. But if you give 17 hints, then it is possible to find Sudokus that have exact grids that complete in a unique way to a full Sudoku. This gentleman, Australia, yes, from Australia, Gordon Royal, found 47,621 Sudokus that are distinct. Distinct meaning you cannot obtain one from the other, and I will mention that in a moment too, how, by some simple operations, symmetries, renaming, and so on. He found 47 Sudokus of that sort. You can find all of them here, so you can download them and you can see if DLB can solve all of them, and I can assure you that it can. How hard are they, these Sudokus? Are they hard? I know that they are not too hard for DLB. Why? Because in late 2005, when there were only 24,270 such 17-hint Sudoku problems, Ines Lims and Wackline, maybe, I'm not sure how to pronounce this name, they showed experimentally that all these Sudokus can be solved by already 2 basic rules, by Boolean constraint propagation with look-ahead. Large number of these minimal Sudokus can be solved just by Boolean propagation. So I know that DLB will solve them because you surely do just Boolean propagation, you do much more. So all of them will be solved. But for humans, unfortunately, it's not so easy, because when a look-ahead is involved, you have a little bit of a trouble there. Okay, and that will be one of the last things I think I will tell you. There is, I will skip counting because I should finish soon, I presume. Is that right?
Yeah, as you like.
As you like, of course. But, yeah, so we will see. One of the nice things here is that given an order n Sudoku, to decide whether it can be completed to a Sudoku grid is NP-complete problem. It is a very simple reduction, so I will show it. Already in 1984, Latin square completion problem, which happens to be perhaps even, you used it perhaps for some benchmarking. It's very often used as a benchmark problem for constraint satisfaction techniques and for sub-techniques. This is an NP-complete problem. It was already shown in 1984, as I said, by Colburn. And we will show NP-completeness of Sudoku by constructing a reduction from this problem. That it is in NP is obvious because it's very easy to once you guess a solution, it's very easy to verify that no constraint is violated. Okay, so how do you prove this NP completeness? Well, look again at the Sudoku that I constructed some time ago. This construction was general. I mean, it worked for every n. I illustrated it with 3. Okay, look at these 3 columns. You see everywhere here there is 1, 1, 1, 1, 1, 1, 1. And these first digits form a Latin square. Okay, so we forget about it for now. There is nothing here. They used to form a Latin square. Okay, this is the Latin square that was here. But you see what, since all these are 1s, if I scramble that and produce a different Latin square and put it back here, I still have a Sudoku grid. Because what I need here is just 3 different positions. What I need here for everything to be fine are 3 different positions. So as long as I have a Latin square here, I can merge it into this picture and obtain a Sudoku. Okay, I put it back. Now I have a Sudoku. Okay, if I forget about some of these numbers and I don't put them here, what I have here is an instance to a Latin square problem, square partial field, and here Sudoku partial field. And now you see, if I could solve this Sudoku, if I could complete this to a full Sudoku, I could take these values, put them here, and I would have a Latin square. So I could solve the Latin square problem. Yeah, and that's the proof of the NP-completeness here. Right? So I now told you how to solve this Latin square completion problem by means of Sudoku completion problem. You have to use this construction. You essentially almost never use this huge part of the big Sudoku. So there may be a smarter construction possible, but still this does the job. Very quickly about counting. This is very interesting because Sudoku counting is a great example if you ever teach group theory and want to explain, for instance, about OR bits and so on in groups, then counting Sudokus provides a beautiful example. So how people counted Sudokus? Well, first of all, they fixed this, okay? Because, of course, you always can renumber so that it's 1, 2, 3, 4, 5, 6, 7, 8, 9. And they were counting number of Sudokus with this square fixed. Then you multiply by n factorial. Having this fixed, they computed the number of ways you can extend that to a Sudoku in this band. And there are many ways. So they didn't count all of them because there are really very, very, very many ways. But all they cared was to know how many essentially different ways there are. A different way of extending this would be if this now extended into a different number of ways to a full Sudoku. So 2 different extensions here that give you the same number of extending down there would be counted as equivalent. They were able to count how many such classes there are. Turns out that only 44. So for each of these 44 classes, all they had to do was to see in how many ways a representative from each of these classes extends down to these 2 bands. And that, for that, brute force was already enough, because you have 44 classes, and then you have so many degrees of freedom removed that brute force works. And this is the number, so it's roughly 6 times 10 to 21.
These are good Sudokus.
What?
These are good Sudokus.
No. These are completed grids. Completed grids. There are fewer good Sudokus, but completed grids. Okay, but many Sudoku grids are essentially identical, right? Because you can renumber them, plus there are symmetries. You can permute the 3 stacks, and you still have a Sudoku. You can permute 3 bands, and still you have a Sudoku. Essentially the same. from the point of view of fun when solving it. Then you can permute 3 columns within a stack, 3 rows within a band, and there are reflections and rotations. If you take all these symmetries, that's where group theory comes into place, and there is a very nice package of programs for processing groups based on generators and finding generators and so on. You end up with many fewer, let's see, 10 digits, okay, so many fewer, essentially different Sudokus. Still enough for me never to be able to solve all of them, I am pretty sure. Okay, and just, so what are things to think about? Can we predict how hard the Sudoku will be? What does it mean that Sudoku is hard or easy? Is there an order 3 Sudoku that cannot be solved by basic propagation with look at it? I don't know. So you have 9 by 9 Sudoku, which is a good Sudoku. Can it be that you will not be able to solve it with look ahead, with BCP with look ahead? For these 46,000 we know that we can. Well, we don't know, but I'm pretty sure we tried it for this 25,000 earlier. Very likely we can, but of course maybe some non-minimal ones are harder for some reason. We don't know. Yes. So just knowing, so if you don't know that it is a good Sudoku, and now we are talking about an n by n case, we know that the problem of completing is anti-complete. But is it still anti-complete to decide that something that you know is either unsolvable or a good Sudoku? That means that there is at most one way of completing. Is it still anti-complete? That's also not known. There are various variants, and there are some references, and I will just show you so that you can appreciate that it is really quite crazy right now. Here is the booklet from the competition from 2007, okay, instruction book. 10 points for this type of a Sudoku. Then you have ISO Sudoku. Then you have parquet version. Then you have Little Killer, okay? Then you have Lucky 7. Then you have stars. You have twin Sudokus. You have things where distances are given, okay? So you, between 3 and 7 in this column, the distance must be 5. Okay? And different types, they have to sum up to something, okay? To 17 somewhere. Okay? And beautiful. Diagonal Sudoku. So you have additional constraints. No repetitions here. Let's just look at shapes. You know how pretty it is? It's just phenomenally pretty. Oh, still something else. Part 3.
So one has to compete in each category?
No. They will then prepare some selection of it, because it's really, I think, superhuman to be able to solve all this. And this double time. And let me get to the point. That's not what I wanted to show. And there are team competitions. So lastly, and I have no idea quite how they do it, but for neighboring Sudoku, so you have to be with pairs, lots of other stuff. So it's enormously now elaborated, but one big thing is this: to generate puzzles of each of these sorts, they use a huge range of custom-made techniques, each for specific problem. But our tools essentially require that you write a different encoding for the constraints, and this basic algorithm that I presented earlier is sufficient to generate essentially all of the puzzles. All you need to change is few lines of code in the program in which you describe constraints. And you can essentially have all of these types of puzzles generated. All right, that's it for...
Thanks for the interesting. Is there any question?
Are those results dependent from the encoding you use?
Pardon me?
encodings? Because you said I need only Boolean propagation plus, and sometimes Boolean propagation plus. Is this dependent from the encoding of this Sudoku stuff or not?
I don't think so. I think that no matter what Sudoku encoding you propose, as long as it is not something completely, again, counterintuitive, which perhaps does encode some of the other indirectly propagation rules, it will still be the case that BCP plus look ahead is sufficient essentially for anything of interest.
So, actually, is it possible to add something into the encoding in order to obtain this
more complex rules?
Yes.
Yes, of course. So this, for instance, rule, one can encode rules that do this some sort of reasoning by cases.
Yeah.
You know that this has to be somewhere, and you can derive certain things that you can, with a little bit of effort, because unfortunately a lot of structured geometry has to be taken into account. But you can encode these rules into the code, and then your solver again is doing these with more stronger propagation rules. Of course. Yes?
As far as you know, is there any competition for automatic solvers of Sudoku?
No, I don't think so, but this is a good point, of course, in that we would have to move up now to 36 by 36, or maybe 25 by 25 already would be quite difficult. 9 by 9 is not a challenge for any of the tools that I am aware of. It's just too simple. Then, again, I have no experience with DLD's grounder in this respect.
So let's move to 64, so that we are the only one that can ground.
Exactly. Let's move to 64, and that's the challenge, and then we can have competition. And I think our tools, quite frankly, would be probably very competitive because they subsume a lot of rules that people would invent specifically for this domain. It so happens that they are quite powerful, and whatever couldn't be, we still could encode that relatively easily with the programs. So, yes?
No, again, I'm counting. Once given a brief, how many minimal schemes you can produce?
So far, those with 17 hints, they are still looking for more. But of course, now finding each next is harder because they already found so many. So I don't know how many minimum schemes, sets of hints you can have. We now know of these 40-some thousand, yes. And they are all available. And by the way, I mentioned it, but I really want to stress it. Many of them can be solved without look-ahead. So these are fantastic Sudokus for humans because they really can be solved in a very simple way, and you have a lot of pleasure because how you measure the pleasure? You have 81 squares, right? And you have to solve as many little problems, as there are free squares. The more free squares there are, the more fun with this Sudoku you will have, right? If there is only one square left, then immediately it's done and no fun at all.
So your solver is available on the web, right?
Our solver is available, but as far as generating Sudokus, I would have to give you, I have here with me source code, I believe, and I could give
So I
it.
guess you told us that you tested it on all the
somebody from Portugal did, in essence. But she says what rules she uses. She uses BCP plus lookahead, so I know that our tool will also solve all those. So yeah. I have here the tool that we use to generate Sudokus. So I can, if you stop by my office, I can show how it works, and eventually you can install it in your machines. When you go for a conference, you just print out 20 Sudokus or 10. And first of all, flying over the ocean takes no time, because you really want to solve those Sudokus. And secondly, the more boring talk, you don't have to worry what to do with time, you just keep on solving Sudokus. That's what I do now when I travel. I always generate for myself 20-25 Sudokus. Unfortunately, here I am so busy that so far I solved only 2. That is actually a measure of quality of the visit. Yeah. If I solved already 15 or 20, I would be worried. That means I have nothing to do and it's a problem. But it turns out that I'm quite busy.
So since you mentioned it many times, possibility to solve this by the idea. I want to tell you my experience
Go
with
ahead.
that. So 2 years ago I was writing a program for solving Sudoku. It was not a choice, not fun, but a family obligation because my father was asking help and I was unable to. So then,
Just a question. You said that Sudoku is just
We can maybe next
So then, no, this is related to what you were saying. I mean, I was tracing the computation. So in 90% of the case, I was checking the computation only on the very hard ones. I mean, those which are classified as they are. In most of the cases, something like 80% perhaps, the idea was solving that only with the deterministic consequence operation, that is the propagation.
Sure.
Only in some cases, it was using one level of look-aheads. It never happened, to those I tried, that it reached the non-deterministic part of the computation. So this is consistent with exactly what I did a very simple encoding that corresponds to your stat encoding. That is just only the 3 constraints. I mean, only 1 digit per row, only 1 digit per column. All digits must be in 1 row and 1 column, and only 1 digit in a square.
Right.
So basically, this I mean,
Exactly.
the experimental computation.
So it seems to me that if we run now this program on all these 47,000 Sudokus or so, we would see that the program solves all of them. I am quite certain.
Yeah.
We would see that large percentage is solved without getting to this first level of guessing, essentially, of look ahead. But one Sudoku among those that I was solving, I found one Sudoku that I couldn't solve, and this is because I think this Sudoku actually did require multiple. Well, it's gone now. Unfortunately, what we produce online is clear, but this would be not a very good one to see. Yes. It very well maybe that I was simply stupid, that I didn't see the right place to make the guess. It's still possible. But typically I would, I got pretty good at these Sudokus that require making a guess. That means doing this conflict, this look ahead, and so this I failed. And therefore, I think that maybe it was a bit harder and required more guesses. I don't know. But knowing what you said, I will be now collecting those that I failed.
That's your failure or look at all
the question.
You said that Sudoku is essentially a set problem, no? But what about the some techniques we have to solve set problem in order to solve Sudoku? I mean,
using set solvers, you mean?
Yeah, random walk, for example, something like this.
Well, so yes, people are using set solvers, of course, for that as well. Ines, in particular, Linz used in her work set solvers only, with various degrees of sophistication based on the propagation rules. From the point of view of solving Sudokus, set solvers are equally good as anything else here, I would say, even better perhaps. But if you think now about the effort you would have to go through in order to generate a Sudoku, then you immediately see the power of tools such as those that we develop. So I think that for solving, it makes no difference what you use pretty much, because ultimately this is a relatively simple such problem. But how these people generate Sudokus for newspapers? They do write programs. In fact, Sudoku became popular only because a retired financial manager from Hong Kong knew a little bit about programming, so he wrote a program to generate Sudokus and had enough of this marketing skill that convinced, I don't remember whether it was Times in London or Daily Telegraph, to start publishing daily the Sudokus. And that's how it really picked up. So he wrote a program. He wrote by hand, all these rules that I was presenting, some of them, he encoded into the program, and then he followed essentially the same algorithm as I presented. Well, we don't have to worry about these rules and so on. They are already encoded very nicely in our solvents. All we need is these 4 lines encoding constraints, and right away you can pretty much generate Sudokus. So that's where the power is. If they, in a sense, contracted us to prepare the next championship, I'm pretty sure we could fairly easily take all these types of Sudokus. Maybe not all of them would lend themselves easily to our tools, but majority would. And we would be able to produce such a brochure relatively quickly. Power of declarative programming.
Just the last one. Is there a characterization of the class of subdistances that you can solve, say, with BCP plus UK?
I don't know.
Or other?
Yeah. I just don't know. That's a good point. And I presume that
polynomial class.
yeah, it's a polynomial class, of course. And there are many known polynomial classes, and in fact there are classes for which you ask characterization. There are classes where unit propagation suffices. Okay?
Like
Horde. Exactly. But of course these are sufficient conditions. If you have this, and this, then unit propagation will do it. But there are very few results, and you also have classes that can be solved by look-ahead. So there are examples of non-trivial classes solvable by these techniques, but no characterization.
It looks like a semantic condition. So
Exactly.